All right, Calculus BC students from across the Yes Prep system and beyond. When we met at the BC Summit a little over a week ago, I talked about the fact that I was planning to record a video specifically going over all the various error analysis tests that we use with series. That's what we're going to do right now. So let's make sure that we're clear, that we're on the same page when I'm talking about the error with a series. So let's say I've got some series. I'm going to sum my a sub n's from 1 to infinity. If this series converges, and that's usually our first question, does the series converge or does the series diverge? If the series converges, well, it converges to an actual number, a true value. That true value is what we call S. That is the actual value I would get if I could actually sum up all of these terms, all infinitely many of them. That's usually not possible. So instead, what we do is we say, okay, well, let's look at A1, A2, A3, ... a sub n, and then you've got the terms that come after it. Sometimes what you're asked to do is a partial sum. You say, well, the true sum over here is big S. What I want to do is what we're going to call a partial sum. And so if I sum up the first n terms, this is S sub n. This is the nth partial sum. We're going to call it a partial sum because I've only added up a finite number of terms, so that's why it's a partial sum. It's the nth partial sum because we've added up the first n terms. Everything that I didn't add up, that is my remainder. Okay? So when I think about the error is the difference between your true sum, big S, and your partial sum, S sub n. Now that error could be positive, it could be negative. I'm sorry, the difference could be positive or could be negative. Usually when we talk about error, we talk about the absolute value. The error is the absolute value of the difference between the true sum and the partial sum. Now, what we try to do through these various techniques that we're going to look at is get a bound, is get an upper limit on the error that exists between our true sum and the partial sum. And we're going to look at three completely different ways to go about finding an error bound. The first one comes with the integral test. The integral test, remember the integral test is going to work if you have a series that has positive terms, that the function that generates those terms is continuous and decreasing. So if f is positive, continuous, and decreasing for all values of x greater than or equal to 1, and my a sub n's, the terms in my series, are equal to the value of the function, then that sum, the infinite sum, and the integral from 1 to infinity of f of x, well, they either both diverge or they both converge. That's the integral test. The other piece, though, is that if our series converges, then the remainder, that r sub n, the difference between the true sum and the partial sum, is bounded by 0 on the lower end and the integral from n to infinity of your function. So if I'm summing the first 4 terms, for example, the remainder is going to be greater than or equal to 0, but less than or equal to the integral from 4 to infinity of f of x with respect to x. This bound can be proven using some ideas from Riemann sums. We're not going to prove that this error bound works. We're going to assume that it does, and this is error bound number 1, the integral test. You can only use this when your terms are positive, continuous, and decreasing. And your bound is going to be between 0, your error is going to be between 0 and the integral from n to infinity of f of x dx. That's number 1. It's not the most popular one. It's not the one that shows up most often, but it is an error bound. Let's look at a far more common one that shows up on the free response. This is the alternating series remainder. Suppose that a series has terms that are alternating. They're doing that plus minus plus minus. They're decreasing in magnitude. So if I ignore the sign, the terms are getting smaller. And there's a limit of 0. If the series has a sum s, then this time the remainder, the absolute value of the remainder, is less than a sub n plus 1. I want to look at this one more time. Look at this. The remainder, the difference between the true sum and your partial sum, is less than, not some complicated expression like the integral, it's less than the first term that you did not include. That's it. Where s sub n is the nth partial sum of the series. So if your series is alternating, decreasing, has a limit of 0, then your error, using only the first couple of terms, the first 5 terms, well, that error is less than the 6th term. Easy peasy. Now for the scary one. And I'll tell you, the first time I taught Calculus BC, I remember we worked on this for like 4 days in a row, and it finally made sense to me on the 4th day. This one is called, it starts with Taylor's theorem, but ultimately it's the Lagrange error bound. Lagrange is popular on the test. Not popular with the students, popular with the test writers. Okay, if f is a function, differentiable through order n plus 1, means I can take the first derivative, the second derivative, the third derivative, the n plus first derivative, in an interval I containing c, then for each value of x in that interval, there exists a value of z between x and z such that this is true. This sounds like gobbledygook. Stay with me. My function, if I write my function not as a power series, but as a, look at all these terms, f prime of cx minus c, f double prime of c over 2 factorial x minus c squared, f triple prime of c over 3 factorial x minus c cubed, out to f of n, the nth derivative, evaluated at c divided by n factorial x minus c to the n. They're saying that the value of my function is equal to, well, this first part, we're going to call this p sub n. That is the nth degree Taylor polynomial approximation. The value of my function is equal to that nth degree Taylor polynomial plus a remainder. Now that remainder, what Taylor's theorem says is there is a value of z, some z, such that the remainder is exactly equal to the n plus 1th derivative. Think about that. The one more derivative evaluated at z divided by n plus 1 factorial times x minus c to the n plus 1. The original function, the value of the original function is equal to the value of the nth degree Taylor polynomial plus your remainder, where, and that's for some value of z, and z is inside this interval. This expression, the f of n plus, the n plus 1th derivative evaluated at z, divided by n plus 1 factorial times x minus c to the n plus 1, this is known as the Lagrange form of the remainder, or the Lagrange error bound. Okay, we're almost there. One useful consequence of Taylor's theorem is that your error is going to be less than or equal to x minus c to the n plus 1 power divided by n plus 1 factorial. That part should be familiar, right? Those are our coefficients in a Taylor polynomial, times m. And I'm going to define m to be the maximum value of the absolute value of the next derivative on that interval. We're gonna come back, we're gonna look at this one. So here's what I want to do. I've picked 4 or 5 questions. You're gonna have the handout, don't worry. And with each of these questions, we do not have time to work through all of the parts. But what I want to do is get you to the error part so that we can get some at-bats with that. This first one is the only one that we're going to do pretty much in its entirety. So here we go. This question comes from Nancy Stevenson. She's a Calculus BC trainer. Let f be a function that has derivatives of all orders. F of 2 is equal to 4, f prime of 2 is a third, f double prime of 2 is a fifth, f triple prime of 2 is a seventh. The graph of the fourth derivative on the interval 2 to 2.8 is shown at the right. So this is f4 of x, the fourth derivative. Okay. They say that it's increasing. Okay. Find the third degree Taylor polynomial for the function f centered at x equals 2. Well, P3 is defined to be f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared plus f triple prime of 2 x minus 2 cubed. I realize I made a mistake because it should be f prime of 2 over 2 factorial, f prime of 3 over 3 factorial. Now I'm going to go through and plug in my values. So P3 is we take f2, which is what? f2 is 4. F prime of 2 is 1/3 x minus 2. F double prime of 2 is 1/5 over 2 factorial, x minus 2 squared. F triple prime of 2 is 1/7 divided by 3 factorial, x minus 2 to the third. And that's it. That's all we needed to do with this one. That's our degree 3 Taylor polynomial for the function f centered at x equals 2, and we're going to resist the temptation to simplify things like 1/7 divided by 3 factorial. Okay. In part B, it says use your answer from A, this guy here, to estimate the value of f of 2.8. Well, f of 2.8 is approximately what you get when you evaluate your degree 3 Taylor polynomial at 2.8. We're going to get 4 plus 1/3 of 2.8 minus 2 plus 1/5 divided by 2 factorial, 2.8 minus 2 squared plus 1/7 divided by 3 factorial, 2.8 minus 2 the whole thing cubed. F of 2.8 is the true value. It's approximately what I get from using the degree 3 Taylor polynomial and evaluating it at 2.8. What's all this equal to? Nobody cares. Okay. C. Use the Lagrange error bound. There it is, striking fear into the hearts of calculus students everywhere and their teachers sometimes. Use the Lagrange error bound to find the maximum possible error for the approximation made in part B. Okay, so go back to your notes if you need to. Your error is less than or equal to, go back to your notes, this guy here. We're going to look at the fourth derivative evaluated at z divided by n plus 1 factorial times x minus c to the n plus 1. C is the center, x is the value that you are approximating, n is the degree of the polynomial that you're going to approximate, and the z, this is the tricky part. If we wanted to know exactly what the error was equal to, we'd have to find the just right value of z to make this work. But that's actually not what we're interested in. What we're interested in is figuring out the bound for the error. So the bound for the error, let me look at that one more time, is we're going to look at the absolute value of 2.8 minus 2, that difference, raised to the fourth power, because here n is 3, divided by 4 factorial times m. m is the maximum, let me define this. It's the maximum value of your fourth derivative on the interval containing your center out to the point that you're approximating, which is 2.8. And at first you might say, well, how the heck am I going to find the maximum value of the fourth derivative on this interval? Hey, they gave you that graph for a reason. When I look at this graph, what is the maximum value of the fourth derivative from 2 to 2.8? We have an increasing function. The maximum value occurs at that right endpoint. The maximum value is 7. So what I know is that my error is less than or equal to, I don't have to simplify anything here if I don't want to. 2.8 minus 2, the absolute value to the fourth power, divided by 4 factorial times 7. That is the error. That is the maximum possible error that you can have based on your approximation. All right, let's just keep going. Let's see what we can do. All right, second problem. You should have this in your handout. This one is another whopper of a problem, and we are not going to do the whole thing. Okay, we've got, let's see, f of x equals sine of x squared plus cosine of x. Okay, we've got the graph of, what is this? This is the absolute value of the fifth derivative. In part A, we're asked to write the first 4 non-zero terms of the Taylor series for sine of x about x equals 0, and then write the first 4 non-zero terms for sine of x squared. If you know how to work with power series and power series expansions, you know sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, yada, yada, yada. That's not what we're going to focus on here. That should be something that you're comfortable with. They then say write the first 4 non-zero terms of the Taylor series for cosine of x. Cosine of x is the even function. Okay, use the series and the series for sine of x squared found in A to write your terms for f, the original function. Then they ask us to find the value of f6 of 0. Okay, not going to worry about those. Here it comes. Let P4 of x be the fourth degree Taylor polynomial for f about x equals 0. Using information from the graph of y equals the absolute value of the fifth derivative shown above, show that P4 of a fourth, the approximation that I get using the degree 4 Taylor polynomial, if I subtract from that the true value of f at 1/4 and take the absolute value, that's less than 1 over 3,000. Now, the piece that you need, and I'm just going to give this to you so we can further the conversation, is you were asked earlier to find the degree 4 Taylor polynomial. And so the degree 4 Taylor polynomial, here it comes, is 1 plus 1/2 x squared plus 1/24 x to the 4th. That's your degree 4 Taylor polynomial. Okay, so in this question they say find the difference between the value of your degree 4 Taylor polynomial at 1/4 and the value of your function at 1/4. We're using we've got a degree 4 Taylor polynomial, so we're going to use Taylor's theorem. We're going to use Lagrange's theorem. This error has to be less than or equal to, well, how does that work? That is going to be, sorry, having a little bit of a brain fart here. Okay, we're centered at 0, so it's going to be 1/4 minus 0 to the 5th power divided by 5 factorial times m, right? This is your error. This guy over here is what Lagrange says. What's m? M is the maximum value of the fifth derivative for the interval containing your center and the point that you are estimating. So I need the maximum value of the fifth derivative from 0 to 1/4. Well, gosh, what is that? Here's 0, here's 1. Looks like I'm counting in fourths here. At 1/4, I can see that the value of the fifth derivative, or I guess the absolute value of the fifth derivative, at 1/4, I can't tell you exactly what that is, okay? But I do know that if I'm counting by, my scale is 20s on the y-axis, I'm greater than 20 but less than 40, so that this guy here must be less than or equal to 40. So that means that my error, let me go back down to the bottom, is less than or equal to 1/4 to the fifth power divided by 5 factorial times 40. Now, you might say, great, that's less than 1/3000. No, you don't get off that easily. You are going to have to show some work here. It would be a large leap of faith to go from here to 1/3000. Well, what can we do? We can do a little side work. 5 factorial is 5 times 4 times 3 times 2 times 1. That's 120. 1/4 to the fifth. 1/4 times a fourth times a fourth times a fourth times a fourth. 16, 1/16. 1/64. 1/256. 256 times 4 is 1/1024 divided by 120 times 40. There's a common factor here of 40. I can cancel those out. So I've got 1/1024 divided by 3. It's the same as 1/1024 times 1/3. That's 1/3072. Because 3072 is greater than 3000, this fraction has to be less than 1/3000. That's the work that I'd have to do. It all has to do with recognizing that this difference, because I'm working with a Taylor series expansion, that difference, the error, is less than or equal to the, I look at 1/4 minus 0, the point I'm estimating, minus my center, raised to the 1 more power, divided by 5 factorial. Remember, this is how we build our coefficients in a Taylor polynomial, times the maximum value of the next derivative. That's the key here. This has to be the biggest of the derivative. All right, let's look at another one. This question comes from the 2011 BC Form B exam. It's question 6. I got to tell you, series questions are almost always question number 6. There are a couple of exceptions, but not too many. Okay, they tell us that f of x is the natural log of 1 plus x cubed. Okay, the Maclaurin series for natural log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, blah, 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 blah. Use the series to write the first 4 non-zero terms and the general terms of the Maclaurin series for f. This is not what we're going to focus on, but I would expect that that's pretty straightforward at this point. The radius of convergence of the Maclaurin series for f is 1. Determine the interval of convergence. Show the work that leads to your answer. Radius of convergence, interval of convergence, we know how to do that. That's not why we're here. Part C, write the first 4 non-zero terms of the Maclaurin series for f prime of t squared if g of x is the integral from 0 to x of f prime of t squared. use the first two non-zero terms of the Maclaurin series for G to approximate 1. This is where we are starting to get our head in the game. Okay, I want to make quick work of part C because this is not the part we're focusing on. When you've done your work, you're going to see that f prime of t squared equals 3t to the 4th minus 3t to the 10th plus 3t to the 16th, and so on and so on. G is the integral from 0 to x of f prime of t squared with respect to t. You're going to get 3/5 t to the 5th minus 3/11 t to the 11th plus 3/17 t to the 17th power, and so on and so on and so on. It says use the first two non-zero terms, that's these guys right here, to approximate g of 1. G of 1 is approximately 3/5 1 to the 5th power minus 3/11 1 to the 11th power, which is 3 over 5 minus 3 over 11. Again, this is a perfectly acceptable answer. No need to simplify. That's a perfectly acceptable answer. No need to simplify. But let's do a little bit more anyway. 3/5 minus 3 over 11, common denominator would be 55. 33 over 55 minus 15 over 55 is 18 over 55. This is my estimate. It's not my error, it's the estimate. Okay, part D. The Maclaurin series for G, remember G, evaluated at x equals 1, is a convergent alternating series with individual terms that decrease in absolute value to 0. Show that your approximation in part C must differ from G of 1 by less than 1 over 5. What the heck does that mean? Let's think about this. They tell us that the Maclaurin series for G is alternating, individual terms that decrease in absolute value to 0. They decrease in absolute value to 0. Those two things together tell me that the alternating series test applies. Well, what does the alternating series test? Take a minute, go back in your notes if you need to. The alternating series test says that my error, remember the error is the difference between the value of your function at 1 and your estimate. The estimate we had was this 18 over 55. What does the alternating series test tell you about this error? It's less than or equal to the next term. It's less than or equal to a sub 3. Here we are, 3/17 t to the 17th. That's the third term. So my error is less than or equal to 3 over 17 times 1 to the 17th power. 1 to the 17th power is 1. 3 over 17 times 1 is 3 over 17, and 3 over 17 is less than 1 over 5. If you're not 100% sure about that, well, 1 over 5 is the same as 3 over 15, and 3 over 15 is less than 3/17. I'm sorry, 1 over 5 is equal to 3 over 15. 3 over 15 is greater than 3 over 17. You could do it that way. You could just write it. It's probably going to be okay. The key here in this problem is recognizing in part D that because your terms are alternating and they're decreasing in absolute value to 0, the alternating series test applies. And what the alternating series test tells us is that the difference between the value of the function and my estimate is less than or equal to the next term in my sequence, which in this case is 3 over 17 to the times 1 to the 17th power. Okay, let's keep going. All right, friends, this question comes from the 2017 BC exam. It's question number 6. You've got it in your handout, so this is a very recent BC question. We're told in the beginning that f of 0 is equal to 0, f prime of 0 is equal to 1, and f, the n plus 1th derivative evaluated at 0, is equal to negative n times the nth derivative of f evaluated at 0 for all values of n greater than or equal to 1. That may sound like gobbledygook. I know people are making these things up, truly. We're told that a function f has derivatives for all orders, for -1 less than x less than 1. The derivatives of f satisfy the conditions above. The Maclaurin series for f converges to f of x for absolute value of x less than 1. Okay. In part A, show that the first 4 non-zero terms of the Maclaurin series for f are given by this expression right here, x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and write the general term for the Maclaurin series for f. That, I know you've heard me say this a couple of times now, that is not why we're here. B, determine whether the Maclaurin series described in part A converges absolutely, converges conditionally, or diverges. Ooh, fun stuff. Not why we're here. C, write the first 4 non-zero terms and the general term of the Maclaurin series for g, which is the integral from 0 to x of f of t dt. We are going to need that, but I'm just going to give it to you. And then finally, here's why we're here. Let p sub n of 1/2, the nth degree Taylor polynomial evaluated at a half, of g about x equals 0 evaluated at x equals a half, where g is the function defined in part C. I'll give that to you in a bit. Use the alternating series error bound to show that this is true. All right, well, in order to do this, you need to know in part C, and this is the work you would have done, you would know that we have x squared over 2 minus x cubed over 6 plus x to the 4th over 12 minus x to the 5th over 20 plus dot, 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 dot. We're an alternating series, -1 to the n plus 1, x to the n plus 1, n plus 1 times n, plus it keeps on going. Okay, that is g. Why do we need that? Okay, p sub n of a half is the nth degree Taylor polynomial for g, centered at x equals 0, evaluated at a half, where g is the function defined in part C. They want us to use the alternating series error bound to show that this is true. Well, let's see. What does that mean? So if I'm evaluating at 1/2, I'm going to get 1/2 squared over 2. I'm going to get 1/2 cubed over 6. I'm going to get 1/2 to the 4th over 12, 1/2 to the 5th over 20, and so on and so on. -1 to the n plus 1. 1/2 to the n plus 1, n plus 1 times n. If I look at each term, okay, so here's the term for n equals 1, n equals 2, n equals 3, n equals 4. A1, my first term is 1/2 squared divided by 2. My next term is 1/2 cubed divided by 6. 1/2 squared compared to 1/2 cubed, that's 1/4. This is an eighth. 1/8 is smaller than the 1/2. I'm dividing the first one, the bigger fraction, by 2. I'm dividing the smaller fraction by 6, what I'm going to get is that a1 is greater than a2. 1/2 cubed is bigger than 1/2 to the 4th. I take the big guy and I divide by 6. I take the small guy and I divide by 12. My third term is even smaller. The fourth term even smaller. I can see that my terms, the a sub n's, are decreasing. I guess in absolute value if we want to be specific. They are alternating. I can see that plus minus plus minus. 1/2 to the n plus 1 as the n gets bigger and bigger and bigger. 1/2 to big powers gets close to 0. If that's not enough, I'm dividing by my values of n get bigger and bigger and bigger. The a sub n's are approaching 0. All this together means that the alternating series test applies. What does the alternating series test tell us? Remember, that's the one that if we look at the absolute value of P4 of a half, the fourth degree Taylor polynomial, evaluated at a half minus g of a half, this guy here is your estimate. G of a half is the true value. This error, how does the error work? The error is less than or equal to the next term. So in our case, if I'm going to use the degree 4, then I'm going to look at the degree 5 term. That this has to be less than or equal to 1/2 to the 5th power divided by 20. Now, you're going to have to finish off the math here. 1/2 to the 5th. 1/2 times a half is a 4th. Times 1/2 is an 8th. Times 1/2 is a 16th. Times 1/2 is 1 over 32. And I've still got to divide that by 20. That's the same as 1 over 32 times 1 over 20, which is 1 over 640. 1 divided by 640 is less than 1 over 500 because 640 is larger than 500. All right, so that is 4 problems. We've got 1 more to go. We're at the 38-minute mark. Oof. Ooh-wee. Last one. This does not come from the College Board. This is a question that was made up specifically for this conversation with you all. Approximate the sum of the convergent series, the sum from 1 to infinity, 1 over n to the 4th, by using the first 6 terms. Include an estimate of the maximum error for your approximation. Okay, approximate the sum of this series using the first 6 terms. Using the first 6 terms, remember that is a 6th partial sum. S6 is the first term plus the second term plus the third term plus the 4th term plus the 6th term. That is 1 over 1 to the 4th. Plus 1 over 2 to the 4th. If you're wondering where these are coming from, n's equal to 1, 1 over 1 to the 4th. N's equal to 2, 1 over 2 to the 4th. 1 over 3 to the 4th. 1 over 4 to the 4th. 1 over 5 to the 4th. 1 over 6 to the 4th. That's it. That's my 6th partial sum. For those of you that have access to a calculator, you can plug this in, and the value should be 1.081124. Okay, big deal. Didn't do any calculus there. Now we need to include an estimate of the maximum error for your approximation. Well, we have 3 ways that we can determine error. Number 1, the one that we used at the very beginning, we used the alternating series test These terms don't alternate. Can't use the AST. Nope. What else? We could try Lagrange. Lagrange works for Taylor polynomials. This is not Lagrange. But these two, the alternating series test and the Lagrange error method, these are the two popular ones when it comes to the Calculus BC exam. I would make sure that you are comfortable and prepared for those two. What this is going to be is an integral test. Now, in order to use the integral test bound, or in order to use the integral test, you have to pick the right function, f of x. Well, if my series is of the form 1 over n to the fourth, then f of x is going to be 1 over x to the fourth. And there's three conditions. What are the three conditions? I have to know that for x greater than 1, f of x is positive. Is that true? For all values of x greater than 1, raise something to the fourth power, you're going to be positive. 1 divided by a positive number is positive. Great, check. You don't even have to prove it, you just need to write it. Okay, what else has to be true? F of x is continuous. Now you might say, wait a second, this is not continuous. I have a vertical asymptote at x equals 0. True, vertical asymptote at x equals 0. I just need the function to be continuous for values of x greater than 1 because I'm starting my sum at 1. So f is continuous. And the last thing is that f of x is decreasing. Well, you could take a derivative and show that the derivative is negative. Or you could just say, what happens as the x values get big? As the x values get larger and larger and larger, I raise large numbers to the fourth power, that gets big fast. 1 divided by big is small. So these three together tell me that the integral test, integral test applies. What the integral test says, now remember this, the integral test says that your error, okay, the remainder, and we'll talk about the fact in just a second that I don't really need absolute value bars here, has to be less than or equal to the integral from 6 to infinity of 1 over x to the fourth dx. Now, I just said that those absolute value bars don't need to be there. We're using them pretty consistently everywhere else. The reason that I don't need the absolute value bars is that my function is positive. Because my function is positive, my integral will be positive. So this guy here is always greater than 0, and that's going to be true every time you use the integral test. So the absolute value bar is not necessary. You are going to have to do what? You are going to have to integrate this. And let's use this as an opportunity to do this the right way. This is an improper integral because our upper limit is infinity. So we've got an improper integral. Okay. So the right way to do this is you replace the limit that is improper and you say, let's do an integral from 6 to b, and we take the limit as b approaches infinity of 1 over x to the fourth dx. Well, we're going to take the limit as b approaches infinity, integral from 6 to b, x to the negative 4 dx. Power rule, add 1 to the power, divide by the new power. Limit as b approaches infinity, add 1 to the power, divide by the new power. From 6 to b. Clean this up if you want to a little bit. And we're going to get the limit as b approaches infinity of negative 1 over 3x cubed from 6 to b. Evaluating, limit as b approaches infinity of negative 1 over 3 times b cubed minus negative 1 over 3 times 6 cubed. We're taking the limit as b approaches infinity. As b approaches infinity, b gets big. So b cubed is approaching infinity. Times 3, we're still approaching infinity. But we're in the denominator, so that approaches 0. minus this negative is going to be a positive 1 over 3 times 6 cubed. If you're not sure exactly what that is, 6 cubed is 216 times 3 is 648. That is not the value of my sum, that's the error. Okay, this is the maximum error. And I think that's what the question was asking for. A follow-up question, it's not here in the handout, but it could be, is that they'll say, okay, well, if that's the maximum error, can you give me a bound for the true sum being s? Is there a greatest value and is there a smallest value? Well, what do I know? I know that my partial sum was this 1.081124. That was my approximation. My maximum error is 1 over 648. So the biggest s could be is this 1.081124 plus 1 over 648. But the smallest that I could be is, remember my partial sum, all my terms are positive. The smallest that my sum can be is this 1.081124. So my true sum has to be in between these two values. Done. We did it with minimal errors. Congratulations to us all.